Okay, in this video I'm going to show you, I'm going to go over homework problem number 1 from homework 3, and this is NCS 350 Fall 12. And so this problem says that two stations on an Ethernet wire separated by 100 meters, the propagation speed of the voltage pulses on the wire is 200 meters per microsecond, and station A sends a frame of 1500 bits in length at a data rate of 100 megabits per second. So we need to calculate the time needed to get one bit from station A to station B, calculate the total time to transmit the packet from the time the very first bit is emitted from the transmitter until the time when the last bit is received by the receiver, and finally, suppose both stations are on the same collision domain, how long is the time interval between the time the station A starts sending the frame and the time station B can sense that frame that it's on the wire? What happens if B starts to send during that interval of time? Okay, so here's my solution for that. I show stations A and B separated by a distance D, where D is 100 meters. I have my velocity of propagation is 200 meters per microsecond. The length L of the frame is 1500 bits, and the rate, the data rate, is 100 megabits per second. So I'm drawing a little picture, and I'm writing down all of the given quantities with units on them. Okay. For part A, the time taken is a simple distance is equal to velocity times time problem. So d is equal to vt, and t is the distance divided by the velocity, in other words. And I'm going to plug in the distance d is 100 meters, and instead of plugging in a 200 here, I'm going to plug 200 times 10 to the 6th meters per second, because 1 meter per microsecond is 10 to the 6th meters per second. In other words, if it goes 1 meter in a microsecond, it's going to go 1,000,000 meters in a whole second. And so I wrote in here 200 E6 meters per second. And you divide this out, and you get, actually you don't need a calculator. You have 100 divided by 200 gives you 0.5. And then e to the plus 6 in the denominator is an e to the minus 6th in the numerator. So 0.5 times 10 to the minus 6 seconds, or half of a microsecond. Okay, so 10 to the minus 6th is a microsecond. And so we're going to call that t prop. The propagation time is half of a microsecond. To answer part B, which says the total time to transmit the packet, I drew a new picture for this one. I have A and B on at a distance d apart, and I have the time axis coming downwards. And starting at time t equal to 0, A emits the first bit of the packet, and that bit moves in time across with a slope equal to the velocity to station B. But from the time that A emits the first packet, there's a certain amount of time that it takes to emit the entire packet. Okay, and that amount of time is called t packet here. The same amount of time that it takes A to emit the packet is the amount of time that it's going to take B to receive that packet. So I can label it either over here at A or over here at B. In any case, the total time to transmit the packet is equal to the propagation time plus the time to emit or receive the packet. T packet, in much the same way that distance is velocity times time, the length of the packet is equal to the rate, the data rate, times the time it takes to emit it. So this is in bits per second, the rate. T is in seconds, and L is in bits. Okay, so in exactly the same way we can solve for T to get D over V, we can solve for T to get L over R. And here I'm showing how the units on that work out, and I just plug in L and R. L is 1500 bits, R is 100 times 10 to the 6th, which is 100 megabits per second. Notice I've taken the mega and turned it into an E6. And again, we don't need a calculator. 1500 divided by 100 is 15 times 10 to the minus 6th, or 15 microseconds. And so you can see here the total time is half a microsecond plus 15 microseconds, or 15.5 microseconds. Finally, in part C, they're asking about the two being on the same collision domain. How long of a time interval does B have before he starts seeing the packet from A? And the answer is he's got T-prop amount of time. So the time it takes for station B to detect that A is transmitting is T-prop, or half a microsecond. And furthermore, if B starts sending during this time, during that half a microsecond interval, then there will be a collision. Okay, hope that helps on problem 1. Thanks for listening.